In this video, we're going to continue our discussion of the interval of convergence of a power series. The question here is to find the radius and the interval of convergence of the power series summation n equals 2 to infinity negative 1 to the power of n times x plus 1 to the power of n times 3 to the power of n divided by n squared minus 1. We're going to apply the ratio test with a sub n is equal to negative 1 to the power of n times x plus 1 to the power of n times 3 to the n divided by n squared minus 1. Applying the ratio test, we have limit n approaches infinity, absolute value of a sub n plus 1 divided by a sub n. This is equal to limit n approaches infinity. Now plug in n plus 1 wherever we see an n. So we get negative 1 to the power of n plus 1 times x plus 1 to the power of n plus 1 times 3 to the n plus 1 divided by n plus 1 squared minus 1, all divided by a sub n term, that's negative 1 to the power of n, x plus 1 to the power of n times 3 to the n divided by n squared minus 1. Alright, so we're going to simplify this. We'll get limit n approaches infinity, absolute value of x plus 1 to the power of n plus 1 divided by x plus 1 to the power of n. Recall, we're dividing by this fraction, so we're going to flip this fraction. The numerator becomes a denominator, and the denominator becomes a numerator. Multiplied by 3 to the n plus 1 divided by 3 to the power of n times negative 1 to the power of n plus 1 divided by negative 1 to the power of n times n squared minus 1, because the denominator here flips and becomes a numerator, divided by n plus 1 squared minus 1. Alright, let's simplify this expression. So we get limit n approaches infinity. Now, looking at the last page, here we have the same base, so we subtract off the exponents, so we just get x plus 1. And again, here we have the same base, the base is 3, so we get 3 to the power of n plus 1 minus n, we just get 3. And same story here, same base, subtract off the exponents, we just get negative 1. And we're going to simplify this as well. Alright, so doing some simplification, we get x plus 1 times 3 times negative 1 times n squared minus 1. And in the denominator, going back to the last page, you can see that here we get n plus 1 squared minus 1. So if we open it up, we get n squared plus 2n plus 1 minus 1. And we just get n squared. This part just simplifies to n squared plus 2n plus 1 minus 1. And 1 minus 1 cancels out. We just get n squared plus 2n in the denominator. So we get n squared plus 2n. This is equal to limit n approaches infinity, absolute value of x plus 1 times 3 times n squared minus 1 divided by n squared plus 2n. Now, absolute value of x plus 1 doesn't depend on the limit, so let's remove it outside the limit. So we get absolute value of x plus 1 times the limit n approaches infinity, 3 times n squared minus 1 divided by n squared plus 2n. So now, to evaluate this limit, let's divide by the highest power in the denominator, divide by n squared, divide by n squared, and divide the numerator also by n squared. And simplifying this, we're going to get absolute value of x plus 1 times the limit n approaches infinity, 3 times n squared divided by n squared, we get 1 minus 1 over n squared divided by n squared divided by n squared gives us 1 plus 2n divided by n squared gives us 2 over n. When we take the limit as n approaches infinity, 1 over n squared, of course, approaches 0, and 2 over n also approaches 0 as n approaches infinity. So we're going to get absolute value of x plus 1 times 3. Now recall that this is a result of doing the ratio test, limit n approaches infinity, of absolute value of a sub n plus 1 divided by a sub n. And the result we obtain is 3 times absolute value of x plus 1. According to the ratio test, the series converges if the ratio is less than 1. So let's make this less than 1 and find all the values of x for which this series converges. That's how we find the interval of convergence. So we get absolute value of x plus 1 is less than 1/3. All right, so let's simplify that. We have absolute value of x plus 1 less than 1/3. Let's remove the absolute value, so we get x plus 1 is less than 1/3, larger than negative 1/3. Subtract 1 from every term, so we get x is less than 1/3 minus 1, larger than negative 1/3. Let me just rewrite that so it's easier to read. So x is less than 1/3 minus 1, larger than negative 1/3 minus 1. And simplifying this, we get x is less than negative 2/3 and larger than negative 4/3. This power series diverges if the result of the ratio test, which is absolute value of x plus 1, 3 times absolute value of x plus 1, is larger than 1, which means if absolute value of x plus 1 is larger than 1/3. And simplifying this, we get x plus 1 larger than 1/3, or x plus 1 is less than negative 1/3. Simplifying further, we get x larger than negative 2/3, or x less than negative 4/3. So now let's find the radius of convergence. To find the radius of convergence, let's set x plus 1 to the power of n equal to 0. Take the nth root of both sides, we get nth root of x plus 1 to the power of n is equal to nth root of 0, and we get x plus 1 is equal to 0, and we just get x equals negative 1. This is the center of the power series. So how do we find the radius of convergence? To find the radius of convergence, we take an endpoint and subtract it from the center. So radius is negative 2/3 minus 1. That gives us negative 2/3 plus 1 gives us 1/3. Or simply, you can look at the result of the ratio test, x plus 1 less than 1/3. This is the radius of convergence. Radius is 1/3. So let's review what we've done. We found the interval of convergence, which is between negative 2/3 and negative 4/3. The center of this power series is negative 1. The radius is a distance from an endpoint to the center, which is 1/3. So this is the radius. Radius is equal to 1/3. Or you can say negative 1 minus 4/3, so the center minus the left endpoint, and again we get a radius is equal to 1/3. But the ratio test doesn't tell us what happens at the endpoints. At the right endpoint, x equals negative 2/3, and the left endpoint, x equals negative 4/3. We have to plug those points, those endpoints, manually into the power series and apply a test of convergence like basic comparison test, alternating series test, or limit comparison test, and find out what the power series does at those endpoints, whether the power series converges at those endpoints or whether it diverges. We have to look at that separately. All right, so let's check the endpoints. So check endpoints. The left endpoint is x is equal to negative 4/3, and the right endpoint is x is equal to negative 2/3. We have to plug these into the power series and find out whether the power series converges or diverges at those endpoints. So let's plug x equals negative 4/3 into the power series summation n equals 2 to infinity minus 1 to the power of n times x plus 1 to the power of n times 3 to the n divided by n squared minus 1. So we obtain, plugging this in, we get summation n equals 2 to infinity minus 1 to the power of n. Plugging negative 4/3, we get negative 4/3 plus 1 to the power of n times 3 to the power of n divided by n squared minus 1. So we get summation n equals 2 to infinity negative 1 to the power of n. Negative 4/3 plus 1, that gives us negative 1/3 to the power of n times 3 to the power of n, all divided by n squared minus 1. So simplifying this further, we get summation n equals 2 to infinity minus 1 to the power of n times minus 1 to the power of n times 3 to the n divided by 3 to the n times n squared minus 1. So we're simplifying this term. We'll get negative 1 to the n from the numerator, and from the denominator we get 3 to the n, and we'll place the denominator here. Alright, so you can see we have a cancellation. 3 to the n cancels with 3 to the n, and we obtain summation n equals 2 to infinity negative 1 to the power of 2n, because we have the same base, which is negative 1, add up the exponents, divided by n squared minus 1. But negative 1 raised to an even power will always be plus 1. So we get summation n equals 2 to infinity 1 divided by n squared minus 1. Now we have to ask ourselves, does this series converge or diverge? Well, if we look at the general term 1 over n squared minus 1, for large n, this is approximately equal to 1 over n squared for large n. So it's intuitive to apply the limit comparison test. Apply limit comparison test. Comparison test. With the comparison, b sub n is equal to 1 over n squared, and a sub n is a general term of our series, 1 over n squared minus 1. So let's apply the limit comparison test. Let's take the limit as n approaches infinity of a sub n divided by b sub n. This is equal to limit n approaches infinity. A sub n is 1 over n squared minus 1 divided by 1 over n squared. Let's flip the fraction, simplify, we get limit n approaches infinity n squared divided by n squared minus 1. So let's divide by the highest power in the denominator, divide by n squared, divide by n squared, and divide the numerator also by n squared. And we're going to get limit n approaches infinity 1 divided by 1 minus 1 over n squared. Now 1 over n squared approaches 0 as n approaches infinity. So the result is 1. The limit as n approaches infinity of a sub n divided by b sub n is equal to 1, which is greater than 0. Since the limit exists, since the limit as n approaches infinity of a sub n divided by b sub n exists, and summation n equals 2 to infinity 1 over n squared is a convergent p-series. Is a convergent p-series with p equals 2 greater than 1, p equals 2 larger than 1. The given series summation n equals 2 to infinity 1 over n squared minus 1 1 over n squared minus 1 also converges by the limit comparison test. Also converges by the limit comparison test. That means the power series converges at the left endpoint. The power series is summation n equals 2 to infinity, negative 1 to the power of n times x plus 1 to the power of n times 3 to the n divided by n squared minus 1. This power series converges at the left endpoint. What does that mean? That means if we were to plug in the left endpoint, x equals negative 4/3, into this power series, we would have a finite sum. The sum would be finite. If you add up all these infinite terms, we will obtain a finite sum. That's what the convergence means, convergence at a value of x. All right, so now we need to look at the right endpoint. So let's plug the right endpoint, which is x equals negative 2/3, into summation n equals 2 to infinity minus 1 to the power of n times x plus 1 to the power of n times 3 to the n divided by n squared minus 1. So we obtain summation n equals 2 to infinity minus 1 to the power of n times negative 2/3, plugging x equals negative 2/3 plus 1 to the power of n times 3 to the n divided by n squared minus 1. So simplifying this, we get summation n equals 2 to infinity minus 1 to the power of n. Now minus 2/3 plus 1, that's 3 over 3 minus 2/3 is 1/3, so we get 1/3 to the power of n times 3 to the n divided by n squared minus 1. So we get summation n equals 2 to infinity minus 1 to the power of n times 3 to the n times 1 over 3 to the n divided by n squared minus 1. So essentially this 3 to the n is canceling with this 3 to the n. So here's a simplification. 3 to the n cancels with 3 to the n, and we get summation n equals 2 to infinity minus 1 to the power of n times 1 over n squared minus 1. Now, we can certainly apply the alternating series test and show that the terms are decreasing and the limit of the general term 1 over n squared minus 1 is equal to 0, so the series converges by the alternating series test. But let's actually apply the absolute convergence test. So let's apply the absolute convergence test. The absolute convergence test looks at the absolute value of every term. So we get summation n equals 2 to infinity minus 1 to the power of n divided by n squared minus 1. We take the absolute value of every term and add up all the terms. So we get summation n equals 2 to infinity 1 over n squared minus 1. But we proved earlier that this series converges by the limit comparison test. Converges by the limit comparison test. We did that earlier, and our comparison was b sub n is equal to 1 over n squared. So we can conclude that the series that we have, summation n equals 2 to infinity negative 1 to the power of n divided by n squared minus 1 also converges. So what we have shown is that the power series converges at both endpoints, at x equals negative 4/3, the left endpoint, and also at x equals negative 2/3. So include both endpoints for the interval of convergence. Include both endpoints. Both endpoints for the interval of convergence. So the interval convergence of this power series, summation n equals 2 to infinity minus 1 to the power of n times x plus 1 to the power of n times 3 to the n divided by n squared minus 1 is x is less than or equal to negative 2/3. We include the right endpoint, and we also include the left endpoint, negative 4/3. This is the interval of convergence. That means for all values of x in this interval, the power series has a finite sum. We can also write it in interval notation. So a square bracket, that means include negative 4/3, comma, negative 2/3. Also include the right hand point as well, the right endpoint. So we have drawn a diagram for the interval of convergence. So for all x values between negative 4/3 and negative 2/3, the power series converges. For values of x larger than negative 2/3, the series diverges. And for values of x less than negative 4/3, the series diverges as well. So let's write that down. When x is larger than negative 2/3, the power series diverges. When x is less than negative 4/3, the power series diverges. And when x is less than or equal to negative 2/3 and larger or equal to negative 4/3, the power series converges. That means the power series has a finite sum for those values of x. All right, thanks.